Let's see how you guys did. The hard part about x, 1 over x, is you think of a power. And you think of x to the minus 1. And you think, I'll just do my power rule. But the problem is when you add 1 to the exponent, you get 0. And then we're supposed to divide by our new exponent. And then all of a sudden things seem to be very bad. And it's a very hard one to see because 1 over x is connected to the natural log. And in fact, we can add absolute value bars on there. Now, anytime you have a number inside, like if I had cos of 2x and I had to do the derivative, I'd have a chain rule, right? Because first you do the derivative of the outside function cos, and then you would do the derivative of the inside function, which would be 2x. And if the inside function is technically a line, like 2x is a straight line, then what you multiply is just a number, right? The derivative of 2x is just a 2. So whenever you're multiplying by just a number, integration has to compensate for that. So integration will always just divide by that number. Does that make sense? Like the chain rule, if I had, let's go with cos of 2x, then I took my derivative, it's going to be the derivative of cos is negative sine. We do the derivative of our outside function. We kept our inside function the same, and then we would have to multiply by 2. So if we integrate, if I just had the integral of cos 2x, now I'm going to go in the opposite direction. We'll put a dx here to say we're integrating with regard. We have to think, well, what derivative would give us cos? Sine. So the integral of cos is going to be sine 2x, but if I do the derivative of sine 2x, I have a chain rule where I would have to multiply by 2. So in integration, we have to compensate for that and divide. So now, whenever you integrate, you can check your answer by doing the derivative. And in fact, if you get into the habit of checking your integration by doing the derivative, do you see that you're practicing your derivatives and your integration at the same time? Which is not a bad thing. Some of us are like, yeah, that would be good for me to keep practicing that. Right? So I get my answer. I take the derivative of this. Well, the 1/2 would stay out in front. Right? If I take the derivative of this, the 1/2 would stay out in front. The derivative of sine is cos. I keep the inside the same. Chain rule, I have to multiply by a 2. And the derivative of c would be plus 0. And sure enough, those 2's would cancel out. And I get the cos 2x, which I had originally in my integral. So we can always take the derivative of something to check if we've done it right. Okay? Now, if you make a mistake in your derivative, that's going to be a problem, right? Because then you can't really check if you're right if you make a mistake along the way. So we have to be very careful. But it is a good way of seeing how things are going. So here, I have 12 over x. Recognize I have the 1 over x, which is the natural log. That 12 can just be brought out in front. You don't have to write this extra step. I think it'd be fine directly to go to natural log. The absolute value bar is there saying that we can only take the natural log of a positive number. Here, the integral of e to the 5x. We could bring this 1/2 out in front. I'm okay to skip that step and just say, I know I have that 1/2. The derivative of e to the 5x would just be e to the 5x. But you would have had a chain rule here where you would have had to multiply by 5. So we have to compensate and divide by 5. And of course, you could put this together to get 1/10 in the end. And again, anytime you're done, you can do the quick check. If I want to check, I take the derivative. The derivative of this would be 1/10. Derivative e to the 5x would stay e to the 5x. It's a chain rule. I'd have to multiply by 5. Can you see that that will simplify? And when we take the derivative, if it's what we had originally inside of our integral, which it is, then we know we've done it correctly. Again, integral of adding and subtracting, you can do each of them separately. So the first one is just add 1 to the exponent and divide. Second one, the 3 is just a number out in front, and 1 over x is natural log of x. And the third one has a chain rule, right? If you did the derivative, you would have to multiply by 1/3. So when we do the integral, we have to compensate for that chain rule and divide by 1/3. And of course, you could simplify this, but you would not need to, unless it was multiple choice and you're trying to match something up. So sine of 5x, indefinite integral, this is writing it in math. It's called the indefinite because you always have that plus c. You're not quite sure what it is. You know what it mostly is, but we could have a number at the end. So since there's a whole bunch of different answers, that's why we have the word indefinite. Later on, we're going to learn the definite integral. Integral of sine will be negative cos. And you would have had a chain rule here, so to compensate, we have to divide by 5. This compensation for chain rule only works for this kind of chain rule. Any kind of chain rule that has an x involved, then your life is more complicated. But if it's just a number, you can just divide. So like the derivative of the inside function is just 5, so we can compensate by dividing by 5. Right? As soon as we get to this, like if we're at what? This is at level 2 integrals. This bumps it up to level 30 just by adding that 2. Right? This might be one that's like, no, sorry, too hard for this course. Just by adding that 2. Integrals are crazy that way. It's like we're walking a fine line between, yeah, you can do this one. Yeah, you can do this one. Yeah, we can learn a tough technique and we can do this one. And then there's some where like, actually no one can do them. Or no one can do them well. It's like, what? They can get that, yes, they can get that complicated. In fact, we take a whole section of what do you do when it's so complicated that you can't do it? Techniques. So it's kind of, I know it's a little disturbing. You want all math to be doable. But some things get too complicated. Or the amount of math that's required, well, you'd have to go 4 years of university and then beyond.
Can you do that one?
Not right now. That 5x squared inside causes a problem. Because if you did the derivative right, you have a 10x. But if I had a 10x connected to something in a derivative and I'm checking, then I have my product rule, which gets it really big. Oh. Okay. Did we do this one already? No. just saw the 1/3 again. Again, compensation for that chain rule when it's straightforward. So one way you could try to find, like that one that I just showed, try to come up with some sort of original equation that you take the derivative of and you just get sine 5x squared. What would your original equation like? That's one way that sometimes people find complicated integrals, is they just by luck do a derivative one time, they're like, oh, look at this. This is what it's simplified to. But other times, you're like, no, I've never had a derivative that the final answer is just a nice sine of 5x squared. And of course, you could simplify this. Okay. And yes, that was the last one. So, can you see that? Let's just go back to one that we did, so I don't have to, I'm not rewriting things for you. So we did the integral of cos 2x, and it ended up being sine 2x divided by 2 because we had to compensate. Okay? What is, and then we checked it, right? We checked the derivative of sine 2x divided by 2, and sure enough, things canceled out. I'm going to check sine 2x divided by 2, but this time I'm going to add 17. Oh. I want you to do the derivative of that one. Okay, would it be a chain rule again? Yes, because you have something inside. So what would we do? We keep the half, right? We do the derivative of sine, which would be, if I do the derivative, if this is y, then y prime would be, I keep the half. Derivative of sine is cos, keep the inside the same. And then the derivative of the inside, 17. The derivative of the inside is just the 2 again, so it cancels out with that 1/2. Did the 17 make any difference? No. The inside is still basically a straight line. Y equals mx plus b. If your inside function with the chain rule is y equals mx plus b, a straight line, then the chain rule's derivative is always a number. And in those cases, you can compensate by dividing. And that's what we're going to look at in our next section here. Derivatives of the form if the inside is a straight line. So first of all, this is another warm-up. I want you to do the derivative of all of those. Practice your derivative rules. I'll put up the answers in a bit. I'll put up the answers, checking out your derivatives. Did you remember the last one that cos was negative sine and sine was positive cos? So each of these has a chain rule. And the pattern is the same for each chain rule in each place. Right? We do the outside derivative and keep the inside function the same. And then afterwards we multiply by the derivative of the inside function. And in each of these cases, that derivative of the inside function is a constant. It's a single number. with no variables. And this will allow us to integrate each of these easy. Because anytime you integrate and you have a chain rule and the inside function is ax plus b, y equals mx plus b, some line, you can compensate for that chain rule. Anytime that inside function is more than that, you won't be able to. So if we wanted to find the indefinite integral of the cube root of 5x minus 4, first of all, I can write this out and change that cube root to 1/3. I see my power rule, so I think maybe I can add 1 to the exponent and divide from my power rule, but then I would have a chain rule normally, if I was checking, and my chain rule normally would have to do the derivative of the inside, which would multiply by 5. So I also have to compensate for that. So in the end, we're going to add 1 to the exponent, divide by the exponent, and then also divide by the 5 to compensate for the chain rule. And so what we're doing right now is we're developing rules for working backwards that compensate, which are a lot easier than having to try to do the mental math and say, oh, I think there should have been a 3/20 out in front. Right? Because then it's like, oh, there's too much mental math going on. Because I know this 4/3 is going to have to come out in front. I know that I'm going to have to multiply by 5. And I know I have to get rid of that, so I have to have that on the end. It gets a little complicated. So now we have techniques that sort of make it systematic. Systematic things are nice because you can sort of kind of do them without thinking. But we are still thinking about what are the big ideas happening here. Okay? And in integration, we have to compensate for a lot of multiplying and derivatives. Right? If you did this final answer as a derivative, the 4/3 would have to come out in front. Well, we compensated that by dividing by 4/3 when we did the integral. And then I'd have to have a chain rule and multiply by 5. Well, I compensated when I did the integral by dividing by 5. Right now, that function, so when I look at a function, I want to integrate this one. Right now, that function has something in the bottom. So if I was doing a derivative and I have something in the bottom, I'm thinking quotient rule. But we haven't done any kind of integration with quotient rule stuff. So I don't know how to undo that yet. Okay? So at this moment, we're like, well, what can I change this to? So it is in a form that I can do. And I'll use my negative exponent so I can change that to a -8. I see my power rule. Okay? And I'll tell you, sometimes a good strategy for integration is to working backwards through your derivative rules. And then once you get your answer and you're a little unsure, just do the derivative to check. You might have made up a rule or a derivative or an integration rule that doesn't exist. And you'll find that when you take the derivative to find out, oh, this did not work at all. But in this case, I'd be like, okay, I see a power. I want to try my power rule. So I'm going to add 1 to the exponent and divide by that exponent. Then if I did the derivative of this function, I would have had a chain rule that multiplied by 9. So I'm also going to divide by that 9 to compensate for that. And when we simplify this, this is what we get. I probably would have kept the 9x minus 1 to the -7 on top Just because then if I wanted to do the derivative, it would be really easy for me to check. But I could take the derivative of this and find out if I was right. Are we getting ready, used to adding the plus C? Or do some of you think you're going to forget to do that on quizzes and tests? A is super exciting if you see it, super frustrating if you do not. How? We need to know our derivatives so well. Like the derivative of natural log of x is 1 over x. Okay? And x is a line. It's just y equals mx plus b, x is y equals 1x plus 0. We can do the integral of any line on the bottom. But when you see this equation, probably, this is where things are, like your brain, the last thing you're going to think about is natural logs when you see that. Because you just see x's. You're in polynomials mode. And 70 to 80% of all the math that we do in this course involves the polynomials part, because it's the most likely to happen. But we have to be able to see that I have a 1 over x with a bunch of extra numbers. So the 15 is not going to matter. I can pull that out in front. Again, this, sometimes pulling this out in front just helps you see the 1 over x better, but it's not necessary to do this step. So I'm going to have 15. A 1 over x means natural log. Technically, add my absolute values there. And then, because the derivative of this would have a chain rule where I'd have to multiply by 3, I have to compensate by dividing by 3. Besides the inverse ones, which are always hard to do either the derivative and obviously the integrals, the natural log is the hardest one to see because it's the least, it looks the least like its original one. Like when I see this next one in B, I'm like, ooh, an e to the x. Its derivative is e to the x. My answer is probably going to have an e to the something in it. It's a little bit easier to see that. Again, you could pull the 7 out if you wanted to. The derivative of the e to the x is keeping it the same. So I keep everything the same, but then I think, well, if I did this derivative, I would have a chain rule where I'd multiply by -3. So I need to divide by -3 to compensate. So now integrals are like little puzzles. They're little puzzles checking how well you know your derivative rules to see if you could work backwards. And the fact that they get so challenging, for some of you, that's exciting. For others, it's like, oh no. Okay? I hope you keep it like, oh, keep it as exciting. There's going to be challenges. And it's so exciting to hear there's ones that people can't do. Because then I feel good at the ones I couldn't do. Even though later I should have been able to do that, but that's okay. Right? It's nice to see that, I don't know, that challenge is exciting. All right, 2 more examples with sine and cosine. Since the derivative of cos is negative sine, that means the integral of sine will be a negative cos. Again, you can skip that first line if you want. That constant out in front will just stay out in front. But now I'll have the negative 3 cos 6x minus 7. And of course, because I would have had a chain rule that multiplied by 6, I have to compensate and divide by 6. And then I have to remember to add the plus c. And one more. Derivative of sine is positive cos. So the integral of cos is positive sine. So the integral of negative cos would be negative sine. But you can just pull that negative out. And you have to compensate. And that's our introduction. Indefinite integrals is just working backwards. But integrals themselves existed before derivatives. So what we did as a working backwards thing isn't where integrals started. Because you can't work backwards from something that was invented after the first thing was invented. That's a little hard to do. Okay? Where integrals started was with areas under curves. And that has to do more with the definite integral as opposed to the indefinite integral. But before we get into all of that, we're going to review sigma notation. This is the Greek letter, capital Greek letter, sigma. Does anybody know what the little sigma looks like? Right? That's a capital. It's like, what the heck? That kid doesn't look anything like its parent.
There's a third one too.
Hmm?
There's a third one.
There's a third one.
Yeah.
I didn't know that. What does it look like?
Like an S.
Like an S? What? That sounds like an American version of making a sigma. Like, oh, these are too hard. Let's rechange the Greek alphabet to just call it an S. Maybe. I'm not sure. Okay. Evaluate the following. So what is the sigma notation used for? It's used for sums. If you have the sigma notation like this, of k equals 1 to 4 of k squared plus 3. This on the bottom is your starting number. We're going to start when k is 1. We're going to go up by 1 until, I don't know if ending is a adjective, an ending number. The number you end at. It can often, if you start at 1 and end at 4, you will do 4 numbers because you go up by 1 each time. Okay? But if you start at 2 and end at 4, you only do 3 numbers. So I want to point out that some of you are going to think this is how many numbers you do. That is not true. In this case, there happens to be 4 because we started at 1. But you can have sigma notation that starts at 99 and goes to 100. Then you will add up 2 things. You'll plug in 99, see what you get. You plug in 100 and see what you get, and you're done. So the number on the top doesn't say how many things you're adding. It just says this is where you will stop. You will start at 1. Then do 2, then do 3, and when you get to 4, do 4, and then stop. So maybe ending number or stopping number. And the inside is the formula. So I put in my first number 1 into my formula. I would get 1 squared plus 3. Then I put in my number 2 into my formula. And I would get 2 squared plus 3. And then I put in 3. And then I put in 4. And I add those all together. Because the sigma notation says, do each one, add them all together, and get a final answer. And of course, for mathematicians to invent a very convoluted shortcut technique for adding a bunch of sums, it must mean that they had to add up a bunch of things so many times they got tired of writing them all. They're like, what is a way that we can confuse students and make this shorter? Right? That's what math is all about. Making things shorter so that people get confused. No. But it feels that way sometimes, right? Like if you just told me to add these up 4 times, that's not hard. But of course you have to invent some weird new notation using a capital Greek letter, right? So now, if you wanted to add up 1, 2, 3, 4, 5, 6, but you wanted your friend not to be able to get the answer to that question, you're like, aha, I could give them this instead. My starting number is 1. My ending number is 6. And I add them all up. So I plug in 1, I get 1. I plug in 2, I get 2. I plug in 3. Okay. Is this the only way to do it? No. Watch this. You don't have to use K, right? Your friends get good at with the K, you could pick a different letter. What letter would you like me to use? S. So we're going to start at S equals what? I'm going to start at S equals 4 instead of 1. What would my formula have to be in here? If I started with 4, but I want my first number to be 1. S minus 3. That would get my first number as 1. If you plugged in 5, would it get your second number as 2? Where would we have to end? 9. This is also correct sigma notation for this question. Just to bother your friend even further by making it more complicated looking. Right? Did I need to do that? No, but it's not wrong. If you remember this from grade 11 as an arithmetic sequence, okay? In grade 11, you had a sum formula for arithmetic sequences. One of those sum formulas was that you could add your first term and your last term and divide it by 2. So now if you added up your first term, or you add your first term and your last term, for those of you that were in my class, this is what I did as a visual. I wrote the same thing backwards. The first one and the last one add up to 7. The second one and the second last one add up to 7. They all add up to 7. So if I add my first one and my last one, in this case it would be, well, with this number, my first one and my last one would be 1 plus 6. I would get 7. How many times do I get 7? 1, 2, 3, 4, 5, 6 times I get 7. But that would be adding it up twice, so I need to divide by 2. Pretty cool technique for adding things up. It just so happens if you went all the way up to n, well, my first and my last ones would be 1 plus n now. And how many would I have? Well, I have n of them. And we get our first important sigma formula. that adding up all the numbers, 1, 2, 3, 4, 5, 6, up to any number you want, is n times n plus 1 divided by 2. And I just showed you how to create that formula by using a strategy. Okay? So, if you have a strategy to create a formula, if you forget the formula, maybe your strategy gives you a chance to relearn. Right? If you just memorize the formula and you've got it memorized perfectly, no problem, right? But sometimes our memory fails us. On the last test, I even had a couple people beside the formula on the max, that area of a cylinder or a volume of a cylinder. Had a couple people write, "Thank you for giving me the formula," because you didn't remember. Right? If I didn't give you that formula, would that make that question more stressful? And some of you are like, "No, I knew the formula. No stress whatsoever." Some of you are like, "I wish you would have given me the circumference formula too. That would have been helpful." All right, so I did a short proof. The official proof looks like this when you go all the way up to n. And you get n plus 1, put little brackets around these. You would get n plus 1 n times, and that would equal 2 sums, so we could divide. That's the formal proof. I did an informal proof with 1 to 6 and just said, well, if I go up to n, the 6's would change to n's. And life is easy. The next two I'm not going to give you the proofs for. You can add up all the squared numbers. 1 plus 4 plus 9 plus 16. And you get this formula. Kind of cool. N(k) cubed, n times n plus 1 divided by 2. Kind of cool that it's the first formula just squared. And that's a formula for adding up all the cube numbers. Isn't that kind of crazy? This is like, if you look at the normal numbers, if you add up the first two normal numbers and square it, it adds up to the first two cube numbers. If you add up the first three normal numbers, 6, and square it, 27 plus 8 plus 1 is 36 as well. That is just, I don't know. This is one of the reasons I love math. Is like, that's crazy. That's crazy patterns. Why is that happening? What's going on?
Why do we divide by 6 in the second?
That's a good question. We're not going into the proof of this one. But in order for this to work, you have to divide by 6. That's what the formula comes up with. You can look up the formulas for adding up k squared. It's really cool. For my master's thesis, I did some activities with my students, and through the activities I did with my students, we came up with a unique way to prove this. So it's kind of. Okay. Some properties of sigma notation. If your formula is adding two things, you can break it up and do the sigma notation of them separately. If your formula has a constant multiplication, you could bring that out and do this on its own. All right, this is where we're going to end this video here.